Okay, we're going to talk about primitive roots, and I'll tell you on the next slide what they're all about. So, primitive roots modulo m are basically very similar to primitive nth root of roots of unity in algebra or complex analysis, where we know that every nth root of 1 is a power of e to the I 2 pi over n. And so just as that's the case, every number that has no common divisor with a modulus is a power of a primitive root modulo m, as long as primitive roots exist. So whereas in complex analysis you can just take the unit circle, cut it up into n equal angle, and then the number of size 1 that sticks out at the angle 2 pi over n will be a primitive root, meaning it will be a number that, as you raise it to higher and higher powers, captures all the numbers so that x to the sum j is equal to 1. The same thing happens with primitive roots in modular arithmetic, but it may not be the case that primitive roots exist for a specific modulus, and in fact the final result in this presentation will tell us exactly for what moduli primitive roots exist. And so, yeah, we will explore for which moduli there are primitive roots, and the presentation after this one will then use primitive roots, for example, in primality testing, because in the next presentation we are going to prove Rabin's probabilistic primality test. With that, let's talk about the order of an integer. And so if a and n are relatively prime, a is not equal to 0 and n is greater than 0, well then x is the order of a modulo n, and it's denoted order of a modulo n, if and only if x is the smallest number so that a to the x is equal to 1 modulo n. So let's see, how does that go? If a and n are relatively prime, then a has a multiplicative inverse plus, a has a multiplicative inverse, and it can be shown that as you take bigger and bigger powers of a, ultimately you will come back to 1. And as an example, well, if you are looking for the order of 3 modulo 11, what do? You just compute it. So let's see, I'm claiming the order is 5, and we basically, we basically count on our fingers, right? 3 times 3 is 9, times 3 is 27, which is 5, times 3 is 15, which is 4, times 3 is 12, which is 1, and so that means 3 to the 5th is 1 modulo 11. And yeah, I just wanted to show that explicitly because it's really that easy for small numbers, and for large numbers we use a computer, we just have to count things out. Alright, quick theorem: when two numbers a and n are relatively prime, a is not equal to 0, n is greater than 0, then x is a solution of a to the x equivalent to 1 modulo n if and only if the order of a divides x. And the proof of that, well, we go both directions. So suppose first of all that the order of a divides x. Well, then a to the x is a to the order of a to the y, because x is order of a times some y, and that's 1 to the y, and that's of course 1 modulo n, so that was not that bad. For the other direction, we assume that a to the x is equivalent to 1 modulo n. Well, then there are a q in the integers and an r that is between 0 and 1 less than the order of a, so that x is q times order of a plus r. That's just the division algorithm. And that means 1 is equal to a to the x is equal to a to the q times order of a plus r, which is a to the order of a to the q times a to the r. And that's 1 to the q, a to the r, and that's a to the r modulo n. And by definition of the order, because the order was the smallest number greater than 0, so that a2 number is equivalent to 1, r must be equal to 0, because otherwise r would be a smaller such exponent. Okay, as an example, if we're looking for all the solutions of 3 to the x equivalent to 1 modulo 11, okay, let's just keep it as equal right now. Well, the order of 3 with respect modulo 11 is 5, and so that means x solves 3 to the x equivalent to 1 modulo 11 if and only if 5 divides x, so the solutions are all multiples of 5. And yeah, as a corollary to the previous theorem, if we've got two numbers that are relatively prime, well then and a is not equal to 0 and n is greater than 0, then the order of a modulo n divides phi of n, the Euler phi function of n, and that is because by Euler's theorem a to the phi of n is equivalent to 1 modulo n, and by the preceding theorem we know that that means that the order of a must divide phi of n, and that finishes that corollary. Hang on just a second, please. And I'm back. Sorry for the interruption. I just wanted to make sure that I recalled Euler's theorem correctly, and of course, as I was making the slides, I did. These results are correct. Alright, we move on. Next theorem talks about basically something like taking logarithms, which is something that we will talk about a bit more in the next presentation. So if we take a and n relatively prime, so that a is not equal to 0 and n is greater than 0, and if we take two natural numbers that are exponents, then a to the I is equivalent to a to the j modulo n if and only if I is equivalent to j modulo the order of a. And the proof is not that bad. First of all, without loss of generality, we can assume that j is greater or equal than I. And a has a multiplicative inverse modulo n, which means a to the I equivalent to a to the j modulo n is equivalent to a to the j minus I equivalent to 1 modulo n. That's also why I wanted to have j greater or equal than I. And, well, that's the case if and only if, by the previous theorem, the order of a divides j minus I, and that means that's the case if and only if I is equivalent to j modulo the order of a. Okay, now we can define and talk about primitive roots. If r and n are relatively prime, r is not equal to 0, n is greater than 0, then we call r a primitive root modulo n if and only if the order of r modulo n is phi of n. So the order of r is as large as possible. We already know that the order must divide phi of n, so that's the largest the order can be. As an example, well, if we're looking for the primitive roots modulo 11, well, I've already shown you how I do this by counting on my fingers, so you can count with me. Because, well, what do we have? Phi of 11 is equal to 10, and that is because, well, let's see, we are looking at phi of 11 equals 10. If we're going modulo 10, hang on. Okay, yeah, sorry, that's phi of 11, which is 10 because it's 11 minus 1, and 11 is a prime number. I had misread that as the order of 11, which wouldn't make sense because the order of 11 with respect to 11 is not defined, since 11 and 11 are not relatively prime. Okay, so we already know from a previous example that the order of 3 is 5, and that means that 3 is not a primitive root modulo 11. And so now the order of 2 is 10. Let's work that out. 2 times 2 is 4, times 2 is 8, times 2 is 16, which is 5. Times 2 is 10, and that gives us that 2 to the 5th is 10. That means that the order of 2 is at least 5, and the only other number that is greater than 5 that divides 10 is 10, so that means that the order of 2 with modulo 11 is 10. The order of 4 is 5, well, sure, because if 2 to the 10 is 1 modulo 11, then 4 to the 5 is 1 modulo 11, and it can't be anything less, because otherwise the order of 2 would be less. The order of 5 modulo 11 is 5. Well, let's see, 5 times 5 is 25, which is 3 times 15 times 5 is 15, which is 4. And times 5 is 20, which is 9, and times 5 is 45, which is 1 modulo 11, and that was 5 multiplications. The order of 6 is 10. Let's see, 6 times 6 is 36, which is 3, times 6 is 18, which is 7, times 6 is 42, which is 9, times 6 is 54, which is not 1, and again we have 6 to the 5th not being 1 yet, so that means that the order must be 10. The order of 7 is 10. 7 times 7 is 49, which is 5. Times 7 is 35, which is 2. Times 7 is 14, which is 3. Times 7 is 21, which is not 1, and again we have 7 to the 5th, and that means the order must be 10. The order of 8 is 10 again. Well, let's see, 8 times 8 is 64, which is 9. Times 8 is 72, which is 6. Times 8 is 48, which is 4. Times 8 is 32, which is not 1, and again we have the 5th power, and the 5th power is not 1 yet, that means it must be the 10th power. The order of 9 is 5, and that comes from the 3, right? Because if 3 to the 5th is 1, then 9 to the 5th also is 1, and the only other one it could be would be 2, and 9 squared is 81, which is not 1 modulo 11. And the order of 10 actually is 2, and that's because 10 times 10 is 100, which is 1 modulo 11. And that's all, and now we just check for the ones that have order 10, which are 2, 6, 7, and 8. The order of 1 is 1, yeah, sure. So 2, 6, 7, and 8 are the primitive roots. Okay, let's have a theorem after all those numbers. So when r and n are relatively prime, n greater than 0, r not equal to 0, if r is a primitive root modulo n, then the set of powers r to the j, j equals 1 to phi of n, is a reduced residue system modulo n, so it is the set of all the numbers that have a multiplicative inverse modulo n. And that does make a good bit of sense, because well, we suppose for a contradiction that it's not a reduced residue system modulo n. Well, then, first of all, any power of r has a multiplicative inverse, right? And that's because eventually some power of r is 1. So the only way this could not be a reduced residue system is that there are I and j such that r to the I is equivalent to r to the j modulo n, and we can assume without loss of generality that I is strictly smaller than j. But then the order of r has to divide j minus I, and that would mean that phi of n divides j minus I. This result may only be true for n being a prime number, because we have seen that the order isn't necessarily phi of n. So give me just a second here. Sorry, I'm not yet in the spirit of things, apparently, because of course the definition of a primitive root means that the order of r is phi of n, so this one is trivial. And then phi of n dividing j minus I, that can't be, because j and I are both numbers that are between 1 and phi of n. Okay, so that takes care of that. And as an example, well, if we are looking for a reduced residue system modulo 14 from a primitive root modulo 14, well, the Euler phi function of 14 is 6, and that is because it is 2 minus 1 times 7 minus 1, which is 6. And so a reduced residue system modulo 14 is 5. And then let's see, 5 squared is 25, which is 11 modulo 14. Times 5 is 55, which is 13 modulo 14, if I'm correct. Times 5 is 65, which is negative 5, 9 modulo 14. Times 5 is 45, which is 3 modulo 14, times 5 is 1. Okay, and that is exactly the orbit, as people that call that also sometimes of 5, and it has length 6, which means it captures all the numbers that have multiplicative inverses modulo 14. Okay, so now we're going to talk about the order of a power. So take a and n be relatively prime, a not equal 0, n greater than 0, and let t be the order of a modulo n, and u be a natural number. Then the order of a to the u modulo n is t over greatest common divisor of t and u. And the proof has two parts. First of all, we show that this thing has to be at least a multiple of the order. So we take a to the u and raise it to t over the greatest common divisor of t and u. Well, t is the order of a times u, and that is what we substitute in for t. And then we realize that this is a to the order of a modulo n, and u over this greatest common divisor is still an integer, so we can factor it like that. And that is 1 raised to this complicated looking exponent, but that's 1 modulo n. Okay, so that means that if I raise a to the u to this number, I get 1, and that means the order of a to the u must divide t over the greatest common divisor of t and u. On the other hand, take x so that a to the u to the x is equivalent to 1 modulo n. Well, then the order of a divides u times x, and that means there is a c so that u times x is c times the order of a, and that is c times the order of a divided by the greatest common divisor of the order of a and u, multiplied with the order of a times multiplied with the greatest common divisor of a and u. And, well, I'm just rewriting that a little bit here, I think, because that means u over the greatest common divisor of a and the greatest common divisor of the order of a and u times x is equivalent to c times the order of a divided by the order of the greatest common divisor of the order of a and u. Yeah, I've just divided by this greatest common divisor here. That's not hard at all. But now we realize when you have two numbers and you divide them by their greatest common divisors, then of course the greatest common divisor of the resulting fractions is 1. And that means that the order of a divided by the greatest common divisor of the order of a and u cannot divide has no factors in here, so it must divide x. And that means that the order of a to the u is t over the greatest common divisor of t and u, where t is the order of a. And that is that. And yeah, so what else can we say? Well, we again take an integer and we let r be a primitive root modulo n. Then r to the u is a primitive root modulo n if and only if the greatest common divisor of u and phi of n is 1, and that comes directly from the previous theorem. The order of r to the u is the order of r divided by the greatest common divisor of the order of r and u, which is equal to phi of n if and only if the greatest common divisor of the order of r and u is 1, because of course the order of r is phi of n, and that means this greatest common divisor is just the greatest common divisor of u and phi of n, and that's it already. Next theorem, well, we take a positive integer that has a primitive root r modulo n, and we then claim that there are a total of phi of n primitive roots modulo n, and that goes like this. Well, r is a primitive root modulo n, and that means all primitive roots modulo n are of the form r to the u for some u, because remember the r to the u's form a reduced residue system, right? And anything that could be a primitive root must be in the reduced residue system, so it must be of the form r to the u. The preceding theorem now, right up here, says that r to the u is a primitive root if and only if the greatest common divisor of u and phi of n is 1. And there are phi of n numbers in the set from 1 to phi of n, so that the greatest common divisor of u and phi of n is 1. And that's it for this one. So if there is a primitive root, then there are always exactly phi of n primitive roots modulo n. Okay, now we're going to talk briefly about polynomial congruences, because, well, primitive roots are solutions of the polynomial congruence x to the x to the phi of d equivalent to 1, right, or phi of n equivalent to 1. And if we look at this a little bit more generally, then if we take a polynomial with integer coefficients, and m greater than 1 being an integer, well, then x is called a root of f modulo m. That should be an m, not an n. And now it is an m. So x is called a root of f modulo m if and only if f of x is equivalent to 0. So these polynomial congruences we want to investigate a little bit more. And the first thing we have is Lagrange's theorem, which basically says the same thing as what we already know for polynomials on the real line. It's just that now we're doing it in modulo arithmetic, where we're going modulo a prime number, and from here on out we'll stick very closely to prime numbers. So when p is a prime number and f a polynomial of degree n with integer coefficients and leading coefficient a n not divisible by p, then f has at most n roots that are incongruent modulo p. How do we prove that? Well, we prove it by induction on n. And the base step for n equals 1 is quite trivial, because the only solution modulo p of a1x plus a0 equivalent to 0 modulo p is negative a1 to the negative 1 a0, where a1 to the negative 1 is the multiplicative inverse of a1 modulo p, which is of course standard notation in algebra. For the induction step, we go from n to n plus 1, so we let f of x be a polynomial of degree n plus 1, and we want it to have integer coefficients, and we want the leading coefficient to be not divisible by p. Well, if f has no roots, then there is nothing to be proved, of course, and so we let c be a root of f. And what we then do is we realize that f of x is equivalent to f of x minus 0, which is the sum k equals 0 to n plus 1 ak x to the k minus the sum k equals 0 to n plus 1 ak c to the k. And now we can factor out the sums and the ak. So this is the sum k equals 0 to n plus 1 ak x to the k minus c to the k. And out of this one, we can factor an x minus c. So this is x minus c, sum k equals 0 to n plus 1 ak, that's just kept. And basically x to the k minus c to the k is just x minus c times the sum over all the I and j, non-negative, so that I plus j is k minus 1, x to the I, c to the j. And that's of course all modulo p. And if we set that equal to x minus c times g of x, we realize that x minus c has exactly one root modulo p. You've got three guesses what it is, and it ought to be c. And g, being of degree n, has at most n roots that are incongruent modulo p. And that means f has at most n plus 1 roots that are incongruent modulo p. Okay, so now we consider a prime number p, and we let d be a positive number that divides p minus 1. And we claim that then x to the d minus 1 has exactly d roots that are incongruent modulo p. And the proof is also pretty much computation. We take e so that d times e is p minus 1. Well, 1 is x to the p minus 1, which is x to the de minus 1 modulo p. And that thing has exactly p minus 1 solutions that are incongruent modulo p. And that is because p is a prime number, and so we find a primitive root modulo p and rotate that thing through, and that would give us p minus 1 here. Hang on just a second. Okay, this is what happens when you try to think ahead too far. I'm trying to prove this using primitive roots, but we don't have primitive roots modulo p yet. We will ultimately. But this is of course just Fermat's little theorem, because this equation is true for every number between 1 and p minus 1. So that claim certainly is valid. And well, now we just take x to the p minus 1, which is x to the de minus 1 minus 1. So we take x to the p minus 1 minus 1. And well, that is x to the d minus 1 times the sum j equals 0 to de minus 1 minus dx to the j. That's another one of those telescoping sum things like we had already seen. And the second factor above has at most p minus 1 minus d roots, because it's of order p minus 1 minus d, that are incongruent modulo p, and x to the d minus 1 has at most d roots that are incongruent modulo p, and because the whole thing has exactly p minus 1 roots that are incongruent modulo p, x to the d minus 1 must indeed have exactly d roots that are incongruent modulo p, and the other factor must have exactly p minus 1 minus d roots that are incongruent modulo p. All right. Another lemma. Take a prime number, and when d divides p minus 1 and is positive, we let f of d be the number of positive integers less than p whose order modulo p is d, and we claim that then capital F of d is smaller or equal than Euler phi function of d, and in fact on the next panel we're proving that they're going to be equal, but we first need the inequality. So the proof is, well, let d be positive and divide p minus 1. If there is no positive integer whose order is d, well then of course f of d is 0, which is smaller or equal than phi of d. Otherwise, when the order of x is d, well then x squared and so on, they're all pairwise incongruent solutions of x to the d minus 1 is equivalent to 0 modulo p, and by the preceding theorem that means these are all the solutions of x to the d minus 1 equivalent to 0 modulo p, and that means from an earlier theorem we get that the order of x to the u, well the order of x to the u is the order of x divided by the greatest common divisor of the order of x and u, so the greatest common divisor of d and u in the denominator and d in the numerator, and that means only the powers with greatest common divisor between d and u being 1 have order d, and because all positive integers less than p whose order modulo p is d must solve x to the d minus 1 equivalent to 0 modulo p, there are exactly phi of d such solutions that are pairwise incongruent modulo p, because basically all the numbers whose order is d will be among these guys, and among these guys only phi of d of them actually have the right order. Okay, so now same hypotheses, p is prime, d is positive, so that d divides p minus 1, and we claim now that there are exactly phi of d pairwise incongruent positive integers modulo p whose order modulo p is d. And now we're going to use stuff that we had done for multiplicative functions and the summative function. So with f of d being the number of positive integers less than p whose order modulo p is d, we have that p minus 1 is the sum over all divisors of p f of d, because after all every number between 1 and p minus 1 has some order d that divides p minus 1. And now it is p minus 1. F of d is less than or equal than phi of d, so this is less than or equal than the sum over all d that divide p minus 1 phi of d, and we know from a theorem about the Euler phi function that that is actually p minus 1 now, and that means that the two sums are equal, and we're going to use the previous lemma again, because f of d is less than or equal than phi of d for all d, we have that f of d is equal to phi of d for all d, because a single strict inequality would lead to p minus 1 being strictly smaller than p minus 1, which of course cannot happen. As a corollary, every prime number has a primitive root, the result that I wanted to tell you and that I wanted to use earlier on, but now we actually have a proof, and that is, well, trivially, d equals p minus 1 divides p minus 1, and that means there are phi of p minus 1 greater than 0 pairwise incongruent modulo p positive integers whose order modulo p is d equals p minus 1 equals phi of p, and those are primitive roots, of course, by definition. Okay, now realize that that is a non-constructive proof, that primitive roots modulo prime numbers p exist. And observations suggest that certain numbers, such as, for example, 2, occur very frequently as primitive roots modulo prime numbers p. And that leads to a conjecture that is not proved. It's a conjecture by R. Tau, which says that an integer a is a primitive root of infinitely many primes if and only if a is not equal to plus or minus 1 and it is not a perfect square. And yeah, that remains unproved. And what we're going to do now is we're going to talk about which types of moduli really have primitive roots aside from prime numbers. And since we already have primitive roots with respect to moduli that are prime, the next natural step is that we look at prime powers. Okay, so we take an odd prime number, and we're going to take powers of 2 separately because they will behave differently. So take an odd prime number and R a primitive root modulo p. Well, then we say that for all k, or then we can prove that for all k in the natural numbers, p minus 1 divides the order of R modulo p to the k. And that shouldn't be too bad. Let's see. The R is a primitive root modulo p, and that means that the order of R with respect to p is phi of p, which is p minus 1. And for every j, so that R to the j is equivalent to 1 modulo p, we have that the order of R must divide j. So by definition of the order, R to the order of R modulo p to the k is 1 modulo p to the k, which means that p to the k divides the difference of R to the order of R modulo p to the k minus 1, which means that p divides that same thing, and that means that the order of R modulo p to the k, when I raise R to that, that's equivalent to 1 modulo p. I think I could have gone directly from here to here, but filling in the details isn't necessarily too bad there. But that means that p minus 1 must divide the order of R modulo p to the k. And yeah, that's what we wanted to prove, right? And that's because the order of R modulo p to the k is one of those exponents, so that R to the j is 1 modulo p. Okay, so now a theorem. You take an odd prime number and take R to be a primitive root modulo p. Then R, or R plus p, is a primitive root modulo p squared. So we're bumping up 1 to 1 higher power, from p to p squared. And well, by the preceding lemma, we know that p minus 1 divides the order of R modulo p squared. And by Euler's theorem, we know that the order of R modulo p squared divides phi of p squared, and phi of p squared for a prime number p, for an odd prime number p in general, is p times p minus 1. And that means that the order of R modulo p squared is between two numbers. It's either p minus 1 or it's p, so it's one of two numbers. It's either p minus 1 or p times p minus 1. And, well, if the order of R modulo p squared is p times p minus 1, there is nothing to be proved, then R is a primitive root. And otherwise, the order is p minus 1, that's the only other possibility, and we will consider R plus p. And R plus p is equivalent to R modulo p, and that means the exact same argument as we just gave shows that the order of R plus p modulo p squared is also either p minus 1 or p times p minus 1. And that means if we can show that R plus p to p minus 1 is not equivalent to 1 modulo p squared, we're okay, and we're just going to use the binomial theorem to multiply out this power. So R plus p to the p minus 1 is the sum j equals 0 to p minus 1, p minus 1 choose j, R to the p minus 1 minus j, p to the j. And what we can see here is we've got a bunch of powers of p in here, which means a bunch of these terms will be 0 modulo p squared, namely, well, we look at the first term, which is R to the p minus 1, that's j equals 0. We look at j equals 1, which gives us R to the p minus 2 times p minus 1 choose 1, which is just p minus 1, plus the sum j equals 2 to p minus 1 choose j, times this product of the powers. And we can see here that now all these exponents are at least 2. And that means that this is R to the p minus 1 R to the p minus 2p plus p squared times the same sum as before, except that this j is now a j minus 2, and that's because we factored out this p squared here. Okay, well, that means this is equivalent to r to the p minus 1 plus p minus 1 r to the p minus 2 times p, because the rest is equivalent to 0 modulo p squared. And that's equivalent to 1 plus r to the p minus 1 is equivalent to 1 modulo p squared. We already knew that. So that's 1 plus p minus 1 to the r to the p minus 2 times p. And that's not equivalent to 1 modulo p squared because p squared does not divide this product. Okay, and so that means that the order of r plus p modulo p squared is not p minus 1, and that means the order must be p times p minus 1, and that's the end of this one. Well, now, as an example, 3 is a primitive root modulo 49. I'll leave it up to you to work that out. Well, okay, we're going to work that out. Yeah, sorry. 49 is 7 squared, of course, and so it's a primitive root modulo 49 because 3 is a primitive root modulo 7, which is something we can check because we would have to check that 3 to the 6th is the first time we get 1. So let's see, 3 times 3 is 9, which is 2 modulo 7, times 3 is 6, times 3 is 18, which is 4 modulo 7, times 3 is 12, which is 5 modulo 7, times 3 is 15, which is 1 modulo 7, and if you've counted with me, that was 6 powers of 3. So 3 is a primitive root modulo 7, we can check that. And 3 to the 6th, well, 3 to the 6th is 9 times 9, which is 81, times 9 is 729. And that's equivalent to 43, which is not 1 modulo 49. And that is because, well, let's see, if I take 14 times 49, I am 14 below 700. And so 14 times 49, 729 minus 14 times 49 is 29 plus 14, which is 43, yes. And that means that the order of 3 modulo 49 is greater than 6, and that means it must be 42, which is 6 times 7, which is phi of 49, yes. Okay, now we continue, and we take an odd prime number, let k and n, then p to the k has a primitive root, modulo p, and moreover, if r is a primitive root modulo p and modulo p squared, then it is also a primitive root modulo p to the k. So that certainly smells of induction. So we take r to be a primitive root modulo p and modulo p squared, and that exists by the previous theorem, because it's either the primitive root r modulo p or it's r plus p, which is also a primitive root modulo p, of course. Well, then we have that r to the p minus 1 is not equivalent to 1 modulo p squared. And we will now prove by induction that r to the p to the k minus 1 is not, times p minus 1, is not equivalent to 1 modulo p to the k for all k greater or equal than 2. And that, of course, will show that this must be a primitive root modulo p to the k, because if this power is not equivalent to 1, then none of the earlier powers is equivalent to 1 either. And that means that r to the p to the k minus 1 times p minus 1 will be the first power, so that this is equivalent to 1 modulo p to the k. I think we'll talk our way through that 2 panels from now. The base step is, of course, guaranteed by the choice of r, and that's because we're going with k greater or equal than 2, and so k equals 2 is already right here. Okay, the highlighting doesn't go too well. And the induction step k going to k plus 1, well, you let k greater or equal than 2 be so that r to p to the k minus 2 times p minus 1 is not equivalent to 1 modulo p to the k. And, well, then r to the p to the k minus 2 times p minus 1 is r to the phi of p to the k minus 1, and that's equivalent to 1 modulo p to the k minus 1. So because that is the case, there is a d, so that p does not divide d, and r to the p to the k minus 2 times p minus 1 is equal to 1 plus d times p to the k minus 1. And that thing we're going to raise to k. So using the fact that p is prime when we drop the sum, we'll see that in just a second, we take r to the p to the k minus 1 times p minus 1, that's r to the p to the k minus 2 times p minus 1 to the p, which is 1 plus d to the p, d times p to the k minus 1 to the p, as we have seen on the previous panel. And that is by the binomial theorem, the sum j equals 0 to p, p choose j, d p to the k minus 1 raised to the j. And now, just as when we did that for the p squared, we have to pull out powers of p, right? And so, well, the 0th term is just 1. The first term, j equals 1, is p times d times p to the k minus 1, because we've got an exponent 1 here. And then we've got the sum j equals 2 to p minus 1. So we're going to treat the pth term separately also. And what do we get here? We get p choose j, d times p to the k minus 1 to the j, all right. We take out a dp to the k minus 1 squared, that gives us d squared p to the 2k minus 2 actually, but we're also dividing this binomial coefficient by p, so we get 2k minus 2 plus 1, which is this 2k minus 1 here. And we can do this division because p is prime, which means p choose j is divisible by that prime number, because nothing in the denominator here can cancel that leading prime number term, and therefore this will be an integer even after we factor out the p. And then we have the last term, which is d to the p, pk, p times p to the pk minus p. All right, and that is equivalent to 1 plus d to the p to the k, and that's because we are going modulo p to the k plus 1. So how does that go? Well, p to the 2k minus 1 is a power more than p to the k plus 1, and so that means that yeah, hang on, that's just, oh come on, I'm trying to do divisibility when I just need a multiple, because okay, so the exponent is greater than k plus 1, which means there's a factor p to the k plus 1 in here, even for the yeah, that's just it. And similarly here, pk minus p is greater than k plus 1, and so that means that these terms are all zeros here. That means we get 1 plus d times p to the k, and remember, p did not divide d, and that means that this is not equivalent to 1 modulo p to the k plus 1. So that completes the induction, and now we're going through this argument that I already mentioned. We take k greater or equal than 2 fixed. By an earlier lemma, we know that p minus 1 divides the order of r modulo p to the k, and the order of r modulo p to the k divides phi of p to the k, which is p to the k minus 1 times p minus 1. So that means the order of r modulo p to the k is p to the j times p minus 1 for some j between 0 and k minus 1. And we have just proved that r to the p to the k minus 2 times p minus 1 is not equivalent to 1 modulo p to the k. And that means for all j's from 0 to k minus 2, we have that r to the p to the j times p minus 1 is not equivalent to 1 modulo p to the k, because otherwise this one here would be equivalent to 1 modulo p to the k. And yeah, and that's what we're just showing here by just factoring things out the right way. And that means that for all j between 0 and k minus 2, the order of r modulo p to the k is not p to the j times p minus 1, and that means the order of r modulo p to the k must be p to the k minus 1, p minus 1, which is phi of p to the k minus 1, and that is what we set out to prove. Okay, so we have worked out that powers of odd prime numbers have primitive roots, Now we're coming to a little bit of the downer part of this presentation, even though it's going to be nice because it's just computations. If we take an odd integer and k greater or equal than 3, another integer, then a to the phi of 2 to the k divided by 2, which is a to the 2 to the k minus 2, is equivalent to 1 modulo 2 to the k, and that means no power of 2 except for 2 and 4 has a primitive root modulo 2 to the k, because, let's see, the only numbers that could be primitive roots modulo 2 to the k are the odd numbers, because the even numbers all have a greatest common divisor of at least 2 with a modulus. And we're showing in this theorem that for all the odd integers, a to the phi of 2 to the k over 2 already gives 1, so nothing ever carries through all the through a whole reduced residue system modulo 2 to the k. Okay, the proof is induction on k. The base case k equals 3 can be checked by checking directly that for a equals 3, 5, and 7 we have that a squared is 1 modulo 8, and that's because, well, yeah, phi of 8 is 4 divided by 2 is 2, and a squared is 1 modulo 8. Well, 3 squared is 9, which is 1. 5 squared is 25, which is 1 modulo 8, and 7 squared is 49, which is also 1 modulo 8, so that works out directly. And yeah, for 1, of course, there's nothing to be done. And now we go from k to k plus 1, so we take an odd integer. Then we have that a to the 2 to the k minus 2 is equivalent to 1 modulo 2 to the k by induction hypothesis. And that means there is a d, so that a to the 2 to the k minus 2 is 1 plus d times 2 to the k, and that d may or may not be odd. But either way, we get that a to the 2 to the k minus 1 is a to the 2 to the k minus 2 squared, which is 1 plus d times 2 to the k from here, quantity squared, and now we just have to multiply out the square. That's 1 plus 2 times d times 2 to the k, which is d times 2 to the k plus 1, plus d squared 2 to the 2k, that's d times 2 to the k squared, and we realize that these two are 0 modulo 2 to the k plus 1, so this is equivalent to 1 modulo 2 to the k plus 1, and that's it already. So that means that powers of 2 don't have primitive roots unless they're 2 and 4. And, well, what else can I say here? When you have that the maximum order of a number with respect to a certain modulus can't be phi of that modulus, then it is certainly natural to also figure out how far the order can be pushed. We have seen that the maximum order of an odd number modulo 2 to the k is 2 to the k minus 1, and it turns out that 5 actually achieves that order. Proof? Well, by the preceding result we already know that the order is less than or equal than 2 to the k minus 1, so we are done if we can show that it's also greater or equal than 2 to the k minus 2. Sorry, I said 1 here. And we'll prove by induction on k that 5 to the 2 to the k minus 3 is equivalent to 1 plus 2 to the k minus 1, which is not 1 modulo 2 to the k. And the base case k equals 3 is again verified via direct computation. And that is because for k equals 3 we're going modulo 8 and we're raising 5 to the first. Yeah, and 5 is not equal to 1 modulo 8. And for the k to k plus 1, take k greater or equal than 3, so that 5 to the 2 to the k minus 3 is equivalent to 1 plus 2 to the k minus 1 modulo 2 to the k. Well, that means that 5 to the 2 to the k minus 3 squared modulo minus 1 minus 2 to the k minus 1 quantity squared. That's binomial formula. That's 5 to the 2 to the k minus 3 minus 1 plus 2 to the k minus 1 times 5 to the 2 to the k minus 3 plus 1 plus 2 to the k minus 1. And the first factor is divisible by 2 to the k, and that's because these two are equal, because this difference is 0 modulo 2 to the k by assumption. And the second factor is divisible by 2 because this is odd, and this is odd, and this is even. And so that means that this difference is divisible by 2 to the k plus 1, and so that means that 5 to the 2 to the k minus 3 squared is equivalent to 1 plus 2 to the k minus 1 quantity squared modulo 2 to the k plus 1, and then 5 to the 2 to the k minus 2 is 5 to the 2 to the k minus 3 squared, which is 1 plus 2 to the k minus 1 squared modulo 2 to the k plus 1, which is 1 plus 2 to the k, 2 times 1 times 2 to the k minus 1 plus 2 to the 2k minus 2, and that's 1 plus 2 to the k, which is not equivalent to 1 modulo 2 to the k plus 1 the whole way. Okay, so now what about the other moduli that are left? We have taken care of prime powers. I think 2 and 4 you can take care of directly, and I don't think we've done that yet, but we will talk about that. So what's left? Well, if you have an integer that is neither a prime power nor twice a prime power, then there is no primitive root modulo n. So that really shows that we've already taken care of most of what's going on. And how does that go? Well, we take n to be the product pj a to the j, where this is the prime factorization, and let r be a primitive root modulo n. Well, by Euler's theorem, we know that r to the phi of pj to the aj is equivalent to 1 modulo pj to the aj. And if we now let n be the lowest common multiple of phi of p1 to the a1 through ps to the as, the lowest common multiple of the pj to the aj, well then r to the n is equivalent to 1 modulo pi to the ai for all I, sure, and that means that it is equivalent to 1 modulo n also, because if every one of these pi to the ai divides this difference, then n divides this difference also. But r is a primitive root modulo n, which would mean that this greatest common divisor, modulo lowercase n, which means that this greatest common divisor, capital N, would be greater or equal than phi of n, and phi of n is the product j equals 1 to s phi of pj to the aj, and that means that no two of the phi of pj to the aj have common divisors, because as soon as they have that, a factor from here would not occur in the lowest common multiple over here. And that means because phi of pj to the aj is pj to the aj minus 1, pj minus 1, that is even for pj being an odd prime. There is exactly one odd prime number, we call it p2, that divides n, and that means that n must be of the form 2 to the a1, p2 to the a2, and suppose for a contradiction that a1 is greater than 1, well, then phi of 2 to the a1, phi of p2 to the a2 is also greater than 1, because then phi of 2 to the a1 will contain 2 to the a1 minus 1 as a factor, which is at least 1, 2, and so then there would be a greatest common divisor of at least 2 here, and so that also cannot happen because those phis were supposed to have no common divisors except 1, and that means any n so that there is a primitive root modulo n must be a prime power or twice a prime power, because any further prime numbers or any higher powers of 2 lead to a contradiction in here. And well, that means if p is an odd prime number, okay, yeah, so now we still have to show that 2 times an odd prime power actually has a primitive root, and so we take an odd prime number, and t being a natural number. If r is a primitive root modulo p to the t, and r is odd, well then r is also a primitive root modulo 2 times p to the t. And if r is a primitive root modulo p to the t and r is even, that's the only other possibility, then r plus p to the t is a primitive root modulo 2 times p to the t. How does that go? Well, we first note that one of r and r plus p to the t is odd, and so we let s be the odd number in r and r plus p to the t. Then s is a primitive root modulo p to the t, because modulo p to the t there these two are both the same. And so that in particular means that the greatest common divisor of s and p to the t is 1. And because s is odd, the greatest common divisor of s and 2 is 1. And that means the greatest common divisor of s and 2 times p to the t is 1. And that means that it has a chance, that s has a chance to be a primitive root modulo 2p to the t. And by Euler's theorem, we know s to the phi of 2p to the t is equivalent to 1 modulo 2p to the t there. And, well, moreover, that means then that for j going from 1 to phi of 2p to the t minus 1, we must have that s to the j is not equivalent to 1 modulo 2p to the t, and that is, well, why is that? And that's because otherwise s to the j is equivalent to 1 modulo p to the t, and j is smaller than phi of 2p to the t, which is phi of p to the t because the 2 doesn't contribute anything here. Yes, sure. Okay, so basically if s to the j if that s to the j was equal to 1 modulo 2p to the t, well then p to the t would divide the difference, so s to the j would be equivalent to 1 modulo p to the t, and j would be smaller than phi of 2p to the t by assumption, but phi of 2p to the t is phi of p to the t, and that is then just not possible. So s is a primitive root modulo 2p to the t, and yeah, that is it, and that is because it satisfies the definition, and raised to phi of 2p to the t, it's equivalent to 1, and if you take anything smaller than that, any power with a smaller exponent, then that's not equivalent to 1. Okay, I'm getting tired, you are probably too, but we're almost done. Because basically what we're saying now is if you've got a natural number n, then there is a primitive root modulo n if and only if n is a number is either 2 or 4 or p to the t or 2p to the t, where p is an odd prime number and t is a natural number. And the proof is very simple. It just follows from all the preceding results, because we've shown that it works for p to the t, we've shown that it works for 2p to the t, we've shown that it doesn't work for anything with more than 2 prime factors unless one of the prime factors is 2 and only occurs in the first power. We have shown that it doesn't work for powers of 2 greater than 8, and well, we can show it directly for 2 and 4. To be honest, I don't want to pause. To be honest, I'm a little tired right now. You are probably too. This has been some pretty tight content here, and so let's finish it from here on out. Well, let's see. Can we quickly do the 2 and the 4? Yeah, a primitive root modulo 2 is 1, because phi of 2 is 1. And if we're looking at a primitive root modulo 4, let's see, phi of 4 is 2, so a primitive root modulo 4 would be 3. Yeah, okay. So that takes care of the whole thing. Get a little bit of rest and then hit the homework problems. We certainly have done something very nice in this presentation, which is we have ultimately completely solved a natural problem, namely the question, when are there primitive roots modulo a certain modulus? And it's now up to you to practice with that a little bit. I'll see you in the next one.